Welcome students, this is Ravi Shankar. In this video we are going to study about the distribution of electrical charges in a conductor and also action of points or otherwise called to be corona discharge. So what do you mean by this distribution of charges in a conductor? So in order to study about this, let us consider two spherical bodies. So I am considering one spherical body, representing it as let the radius of this spherical body, I am taking it as R1. Then I am considering another spherical body B, and the radius of this spherical body, I am taking it as R2. Now, I am considering the distance between the two spheres in such a way that the distance between the two spheres should be greater than that of the radii of each sphere. So while I am placing the two spheres, I have to consider that the two spheres should be placed, in such a way that the distance between the plates, the distance between the spheres should be more than their radii, should be more or greater than the radii of the spheres. It's a condition. Now what I am going to do is, I am joining the two spheres with the help of a thin wire. Now your total charge Q is given to this combination. When a total charge Q is given to this arrangement, a charge of Q1 is distributed over the surface of the sphere A, and a charge of Q2 is distributed on the surface of B. So, on the surface of A, you will be having the charge of Q1 to be distributed uniformly over its surface. Similarly, the amount of charge Q2 is said to be what? Is said to be distributed over its surface. So as we have already studied, inside the hollow sphere we are not having any charge. Now, when you are considering this electrostatic potential, the electrostatic potential on the surface of the sphere A and the electrostatic potential of on the sphere B are considered to be equal. Why? Since both the spheres are being connected with a thin wire. So we have considered two spheres A and B of radii R1 and R2 respectively. The two spheres are being placed in such a way that they are separated by a small distance, and the distance between them is greater than that of the radii of the sphere. To this arrangement, I am giving a charge Q. Before that, the two spheres are being joined with the help of a thin wire. After joining it with the help of a thin wire, I am supplying a charge of Q coulombs to it. When I am supplying a charge of Q coulombs to it, a charge of Q1 is distributed uniformly over the sphere A, and a charge of Q2 is distributed uniformly over the surface B. Since both the spheres are being joined with the help of a thin wire, the electrostatic potential on the surface of A is equal to the electrostatic potential on the surface of B. So we can say the electrostatic potential on the surface of A is equal to electrostatic potential on the surface of B, on the surface of the sphere B. Let us consider electrostatic potential on the surface of A as VA. Similarly, electrostatic potential on the surface of B as VB. Why this is the case? Since both spheres are connected with what? Connected with a thin wire. Since both spheres are connected with a thin wire, we can state that the electrostatic potential on the surface of A is equal to electrostatic potential on the surface of B. So how I can write? I can write mathematically as VA is equal to VB. What is VA? We can say that the potential on the surface of the sphere VA is equal to 1 divided by 4 pi epsilon 0 into Q1 divided by the distance from the center to the surface, let it be R1. Similarly, what is the potential on the surface of the sphere B? It is equal to 1 divided by 4 pi epsilon 0 into Q2 divided by R2. Now, when you are considering the total charge Q, the total charge Q that was being given to the system is separated into Q1 and Q2. So, the total charge can be considered as Q, which is equal to Q1 plus Q2. Now, when you are considering the two potentials, potential on the surface of A is VA and the potential on the surface of B is VB. Both are equal since they are connected with a thin wire. Now, substituting in the above equation, what you can able to get? See, on substituting, I can write it out as that is VA is equal to VB means 1 divided by 4 pi epsilon 0 into Q1 divided by R1 is equal to 1 divided by 4 pi epsilon 0 into Q2 divided by R2. Now we can make a simplification. This 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0 will get cancelled. Now I can write this as Q1 divided by R1 is equal to Q2 divided by R2. But as we know, the surface charge density is charge per unit area. So here I can write instead of sigma 1 surface charge density for the first sphere. Sigma 1 is equal to Q1 divided by the area A1. What is that area? Area of the sphere A. As we know, the area of the sphere is given by the formula 4 pi r square. In this case, the radius of the first sphere is R1. Therefore, I can write sigma 1 is equal to Q1 divided by 4 pi R1 square. Similarly, I can get the value for sigma 2. What is sigma 2? Surface charge density of the second sphere. So, sigma 2 is equal to the amount of charge available in sphere P is Q2 divided by 4 pi, the radius is R2, so 4 pi R2 square. Now, you take this value and substitute for Q1. So, what is Q1 then? Therefore, I can write Q1 is equal to, on cross multiplying, I can write sigma 1 into A1, or I can write sigma 1 into 4 pi into R1 square. Similarly, what is Q2? So how I can write Q2 then? Similarly, Q2 is equal to sigma 2 into A2, which is equal to sigma 2 into 4 pi R2 square. Take these values and substitute for Q1 and Q2 in this equation. So I can write instead of Q1, I can write sigma 1 A1. So I am writing it as sigma 1 A1 divided by R1 is equal to sigma 2 A2 divided by R2. Now I can replace this A1 and A2 with 4 pi R1 square and 4 pi R2 square. So sigma 1 into, what is A1? It is area of the first sphere, 4 pi R1 square divided by R1 is equal to sigma 2 into 4 pi R2 square divided by R2. So on simplifying, one of this R1 will get cancelled. Here one of the R2 will get cancelled. Here you will be getting 4 pi. Here you will be able to get another 4 pi. So what is the final answer that you can able to get? From this I can say that sigma 1 R1 is equal to sigma 2 R2, which is equal to a constant value. See, when you are considering the first sphere as well as the second sphere, sigma 1 is entirely different from sigma 2 and R1 is entirely different from R2. Both are of different values in both cases, but the product of surface charge density and the radius is considered to be equal in both the cases. So sigma 1 R1 value as well as sigma 2 R2 value are same. Or we can say sigma 1 into R1 is a constant with sigma 2 R2. So from this relation or from this I can say in general, I can say sigma into R, product of surface charge density and the radius is equal to a constant. If so, surface charge density is inversely proportional to the radius of curvature. So in terms of wordings, we can write sigma. What is sigma? Sigma is called to be surface charge density. That is amount of charge available per unit area. Surface charge density is inversely proportional to the radius of the sphere. Radius of the sphere. What do you mean by this? As the radius of the sphere go on decreases, as the radius of the sphere go on decreases, then surface charge density go on increases. We can say or we can explain like this. If the radius goes on decreases, that point becomes sharper and sharper. So if the point becomes sharper and sharper, we can say that point has curvature. So this can also be written as the surface charge density sigma is directly proportional to the curvature at that point. Curvature means the sharp point. See, smaller the radius, greater the curvature. Consider like this. You see, that is, if you are considering the radius is smaller, so smaller the radius, then we can say larger is or greater is the curvature. When you are considering a cone, at the sharp end the curvature is higher, but the radius of curvature is considered to be less. So we can say smaller the radius, larger is the curvature, then surface charge density sigma is considered to be what? Surface charge density sigma is considered to be large. This concept we are calling it out as distribution of charges in a conductor. Based on this, we are going to state or we are going to study about an concept called to be action of points, or we can say it out as corona discharge. That we shall see it in our next video. Because based on that corona discharge, I have to go for an example or an illustration. So both of that can conclude one video. So I think you are very clear about this idea regarding the distribution of charges in a conductor. So if you want to recall, I can recall this. So in order to study about the distribution of charges in a conductor, we have to take two spheres of different radii, R1 and R2, and the two spheres are considered to be A and B. The two spheres are now joined with the help of a thin wire. After joining with the help of a thin wire, you supply a total charge of Q coulombs to the system. The charge given is distributed to the two spheres A1 and A and B in such a way that on the surface of A charge of Q1 is distributed, and on surface of B a charge of Q2 is distributed. As we have already studied in the application of Gauss law, that in a case of an hollow sphere, inside that sphere there is no charge residing. So the charges that are being given are distributed uniformly over its surface alone. Since both the spheres are being joined with the help of a thin wire, one can say that the electrostatic potential on the surface of A is equal to the electrostatic potential on the surface of B. So what is the electrostatic potential on the surface of A? The electrostatic potential on the surface of A, let us consider it as VA. Similarly, electrostatic potential on the surface of B, let us consider it as VB. So mathematically I can write it out as VA is equal to VB. The total charge available Q in that system can be written as Q1 plus Q2. So potential on the surface is generally given by the formula 1 by 4 pi epsilon 0 Q by R. Using that we can write potential on the surface of the sphere A as 1 by 4 pi epsilon 0 Q1 by R1, and potential on the surface of B is given by VB equal to 1 by 4 pi epsilon 0 into Q2 by R2. Take these two values and substitute in the above equation. We can write 1 by 4 pi epsilon 0 into Q1 by R1 is equal to 1 by 4 pi epsilon 0 into Q2 by R2. On simplifying, we can cancel 1 by 4 pi epsilon 0 on both sides, and the answer that you can able to get is Q1 divided by R1 is equal to Q2 divided by R2. So Q1 by R1 is equal to Q2 by R2 means, what is sigma? Sigma is surface charge density. As we know, it is charge per unit area. So for both the spheres, the surface charge densities are respectively sigma 1 and sigma 2. So sigma 1 I can write it out as Q1 by A1, and sigma 2 can be written as Q2 by A2. The area of the sphere is 4 pi R square. So I am writing it as sigma 1 is equal to Q1 by 4 pi R1 square and sigma 2 equal to Q2 by 4 pi R2 square. On cross multiplying, we can say Q1 is equal to sigma 1 into A1, that is sigma 1 into 4 pi R1 square, and Q2 sigma 2 into A2, that is sigma 2 into 4 pi R2 square. Substituting for Q1 and Q2 here, I can write sigma 1 A1 by R1 is equal to sigma 2 A2 divided by R2. So substitute for A1, you get sigma 1 into 4 pi R1 square by R1 equal to sigma 2 into 4 pi R2 square by R2. This is R1 and one of the R1 get cancelled. Here R2 and one of the R2 get cancelled, and 4 pi on both sides gets cancelled. And so the next step that we can write is sigma 1 R1 is equal to sigma 2 R2. See, sigma 1 is different from that of sigma 2. And R1 is different from that of R2, but on multiplying by taking the product as sigma 1 into R1 is found to be equal to sigma 2 into R2. So the values are constant. So I am writing sigma 1 R1 is equal to sigma 2 R2 is equal to a constant. Or in general, I can write sigma into R equal to a constant. Or we can say sigma, surface charge density, is inversely proportional to the radius of the sphere. See, in words we can write the surface charge density sigma is inversely proportional to radius of the sphere. That is, when the radius gets decreased, the surface charge density gets increased. Or we can say surface charge density is directly proportional to curvature. Smaller the radius, larger is the curvature, then the surface charge density is also larger. This considered as the distribution of charges over a conductor. Hope you should have understood. Thank you. Let us see in our next video.